The term p-block comes from the type of subshell into which the differentiating, or last added, electron enters. In the modern periodic table, the p-block is located on the right-hand side and includes groups 13 to 18. The name is therefore directly connected with the p-subshell. To understand this properly, we need to understand what a p-subshell is, how its orbitals are arranged, and how electrons progressively fill these orbitals. An atom contains electrons arranged around the nucleus in different energy levels called shells. Within each shell, electrons are arranged into subshells, which are represented by the letters S, P, D, and F. Each subshell contains a specific number of orbitals. The S subshell contains 1 orbital, the P subshell contains 3 orbitals. The D subshell contains 5 orbitals, and the F subshell contains 7 orbitals. Since the P subshell contains 3 orbitals, it has a maximum capacity of 6 electrons. The 3 orbitals of the P subshell are called px, py, and pz. These orbitals have similar dumbbell-like shapes, but they are oriented in different directions in 3-dimensional space. The px orbital is oriented along the x-axis, the py orbital is oriented along the y-axis, and the pz orbital is oriented along the z-axis. Although their orientations are different, these 3 orbitals have the same general energy within an isolated atom and together form the P subshell. Each individual orbital can accommodate a maximum of 2 electrons. These 2 electrons must have opposite spins according to the Pauli exclusion principle. Therefore, because the P subshell contains 3 orbitals and each orbital can hold 2 electrons, the maximum number of electrons that can be present in a P subshell is 6. In simple form, we can write this as 3 p orbitals multiplied by 2 electrons per orbital, giving a maximum of 6 electrons. This capacity of 6 electrons is the key to understanding why the p block contains 6 groups. The filling of the P subshell progresses from P1 to P6. In other words, P1 means that the P subshell contains 1 electron, P2 means it contains 2 electrons, P3 means 3 electrons, P4 means 4 electrons, P5 means 5 electrons, and P6 means 6 electrons. Each of these stages corresponds to one of the 6 p-block groups, from group 13 through group 18. The filling of the 3 p orbitals follows Hund's rule. According to Hund's rule, when electrons enter orbitals of equal energy, they first occupy separate orbitals with parallel spins before pairing begins. Therefore, when the first electron enters the P subshell, it occupies one of the 3 p orbitals. This gives the configuration P1. When the second electron enters, it goes into another empty p orbital rather than immediately pairing with the first electron. This produces P2. When the third electron enters, it occupies the remaining empty p orbital, producing P3, with 1 electron in each of the 3 p orbitals. After reaching P3, pairing begins. The 4th electron must enter one of the already occupied p orbitals and pair with the electron already present there. This produces P4. The 5th electron produces P5, and finally the 6th electron completes all 3 p orbitals, giving P6. At P6, every p orbital contains 2 electrons with opposite spins, and the P subshell is completely filled. The sequence can therefore be understood very simply. P1 corresponds to 1 electron in the P subshell. P2 corresponds to 2 electrons. P3 corresponds to 3 electrons. P4 corresponds to 4 electrons. P5 corresponds to 5 electrons. And P6 corresponds to 6 electrons and a completely filled P subshell. This progressive filling is the fundamental reason behind the 6-group structure of the p block. For the elements of the p block, the general valence shell electronic configuration is written as ns²np1 to np6. The letter N represents the principal energy level of the outermost shell. The S subshell contains 2 electrons. while the p-subshell contains between 1 and 6 electrons depending on the group. This means that p-block elements generally have 3 to 8 valence electrons. Group 13 has the general configuration ns²np⁶. This means that the differentiating electron enters the p-subshell and produces an np⁶ configuration. Therefore, group 13 is the first group of the p-block. Examples include boron and aluminium. Group 14 has the general configuration ns²np⁶. Here, 2 electrons are present in the p-subshell. Carbon is an important example of a group 14 element. Its outer configuration is 2s2, 2p2. This means that after the 2 electrons occupy the 2s orbital, 2 electrons are present in the 2 p orbitals according to the rules of orbital filling. Group 15 has the general configuration ns²np⁶. 3 electrons occupy the 3 p orbitals. Nitrogen is the most familiar example. Its valence shell configuration is 2s2, 2p3. The 3p electrons occupy the 3p orbitals singly before any pairing takes place. This half-filled p-subshell arrangement has special stability and is an important concept in electronic configuration. Group 16 has the general configuration ns²np⁴. The 4th p electron causes the first pairing to occur. Oxygen is an example, with the outer configuration 2s2, 2p4. Its 3p orbitals therefore contain 1 paired orbital and 2 singly occupied orbitals when represented according to Hund's rule. Group 17 has the general configuration ns²np⁵. 5 electrons occupy the p-subshell, leaving only 1 empty position before the p-subshell becomes completely filled. Fluorine is an example, with the configuration 2s2, 2p5. Because it needs only 1 additional electron to reach the stable p6 configuration, halogens have a strong tendency to gain 1 electron. Group 18 has a completely filled p-subshell, represented by ns²np⁶, except for helium, which has the configuration 1s2. Neon is a good example of the p6 configuration with 2s2, 2p6. The completely filled outer shell gives noble gases a highly stable electronic arrangement and is one of the main reasons for their relatively low chemical reactivity. It is important to understand that the p block is not named because the elements have a physical shape that looks like the letter P. The name p-block comes from the p-subshell involved in the electronic configuration. Specifically, the differentiating electron enters a p-orbital. This is the same basic principle used to name the s-block, d-block, and f-block. In s-block elements, the differentiating electron enters an s-subshell. In d-block elements, it enters a d-subshell. In f-block elements, it enters an f-subshell. The position of the p-block on the right side of the periodic table can also be explained through this progressive filling. As we move from group 13 toward group 18 across a period, electrons are progressively added to the p-subshell. Group 13 represents p1, group 14 represents p2, group 15 represents p3, group 16 represents p4, group 17 represents p5, and group 18 represents p6. Once the p-subshell reaches 6 electrons, it is completely filled, and the next period begins with a new principal energy level. For example, consider the second period. Boron has the outer configuration 2s2, 2p1. Carbon has 2s2, 2p2. Nitrogen has 2s2, 2p3. Oxygen has 2s2, 2p4. Fluorine has 2s2, 2p5. Neon has 2s2, 2p6. This sequence clearly demonstrates the progressive filling of the p-subshell across the period. The same pattern appears in the third period. Aluminium has 3s2, 3p1. Silicon has 3s2, 3p2. Phosphorus has 3s2, 3p3. Sulfur has 3s2, 3p4. Chlorine has 3s2, 3p5. Argon has 3s², 3p⁶. Therefore, the p-block pattern repeats in each period where p-orbitals are being filled. One important point is that the p-subshell does not begin filling immediately after the s-subshell of the same principal energy level in the first period. The first energy level contains only the one s orbital, so the first period contains hydrogen and helium but no p-block elements. The p-subshell begins from the second energy level. Therefore, the first actual p-block elements appear in the second period, beginning with boron in group 13 and ending with neon in group 18. There is also an important special case involving helium. Helium is positioned in group 18 because it behaves like a noble gas and has a completely filled outer shell. However, its actual electronic configuration is 1s², not 1s², 1p⁶. Therefore, helium is not technically a p-block element according to its differentiating electron. Its placement in group 18 is based mainly on its chemical properties and noble gas character. This is a useful point to remember for examinations. The idea of progressive p-subshell filling also explains why there are exactly 6 p-block groups. There are 3 p-orbitals, and each orbital can accommodate 2 electrons. Therefore, the p-subshell can contain 6 electrons in total. The possible filling stages are P1, P2, P3, P4, P5, and P6. These 6 stages correspond to groups 13, 14, 15, 16, 17, and 18. So the 6 groups of the p-block are directly related to the 6 electron capacity of the p-subshell. The p-block is especially interesting because its elements show a huge variety of chemical properties. It contains nonmetals, metalloids, metals, and noble gases. For example, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, and chlorine are nonmetals, while elements such as silicon and germanium show metalloid character. Aluminium, tin, lead, and bismuth are metals. The noble gases occupy the final group. This diversity occurs because the number of valence electrons changes systematically across the p-block. The number of p electrons also helps explain chemical reactivity. Elements with p1 configuration tend to lose or share electrons in ways that help them reach a more stable configuration. Elements with p5 configuration are only 1 electron short of a completely filled p-subshell and therefore often have a strong tendency to gain or share 1 electron. Elements with p6 have a completely filled p-subshell and are generally much less reactive. Therefore, electronic configuration provides a direct connection between the structure of an atom and its chemical behavior. The most important idea to remember is that the p-block is defined by the differentiating electron. If the last added electron enters a p-subshell, the element belongs to the p-block. The p-subshell contains 3 orbitals, called px, py, and pz. Each orbital can hold 2 electrons, so the entire p-subshell can accommodate a maximum of 6 electrons. These 6 possible filling stages, from P1 to P6, correspond to the 6 p-block groups, groups 13 to 18. So, whenever you see the term p-block, immediately connect it with 3 ideas. The differentiating electron enters a p-subshell. The p-subshell contains 3 orbitals, and those 3 orbitals can hold a maximum of 6 electrons. As the p-subshell fills progressively from 1 to 6 electrons, the periodic table moves from group 13 to group 18. Group 13 represents np1, group 14 represents np2, group 15 represents np3, group 16 represents np4, group 17 represents np5, and group 18 represents np6. This simple electronic pattern is the foundation for understanding the entire p-block and its position, structure, periodic trends, chemical properties, and reactivity.